NASA just documented a new batch of data on Comet 3I Atlas today. And there's one word that keeps showing up behind the scenes: evolving. Not done, not settled, not fading, evolving. If you've been following this interstellar comet with me and don't want to miss what happens as it keeps changing on its way out of our solar system, make sure you're subscribed, drop a like, and stay with me till the end. Today's fresh numbers don't just tell us what this comet is doing right now. They hint at what it might be turning into. Here's what NASA saw. Today's update started with what should have been the most boring part: routine photometry. New brightness measurements, same filters, same telescopes, same geometry corrections. On paper, the expectation is simple. As this comet moves away from the sun, the heating drops, the activity drops. Its brightness should follow a smooth downward curve. Every new data point is supposed to land a little lower than the last one. The newest points refused. When they plotted today's magnitudes over the predicted fading curve, the real comet sat above it again, not exploding, but clearly brighter than it should be at this distance. It wasn't just a single outlier either. Multiple measurements clustered along a new, slightly higher trend line. The first hint: something inside the comet has changed enough that you can see it in pure brightness. But that's just the surface. The real story is hiding in how that light behaves over time. When the team folded today's brightness data over the last known rotation period, the pattern didn't quite match. The main peak, the moment when the most active regions face us and the sun at the same time, showed up slightly earlier than expected. A secondary bump, which used to be small and inconsistent, has now become a steady, repeatable feature every rotation to get the whole light curve to line up. They had to shorten the period again. This comet has spun up a little more and more. Importantly, the shape of the light curve has changed. A single dominant source of activity has become a more complex arrangement, multiple regions flashing in a predictable order as the comet turns. That's your first clear sign of evolution. It's not just more or less activity. The pattern of activity is changing. Then they turn to the images. Today's deep exposures were stacked and sharpened the way they always are, aligned on the nucleus. So every photon of coma and tail structure can be squeezed out of the noise. If you blink last week's stack against today's, you can literally see the evolution in the older image. The inner coma looked like a stretched glow with a bar of brightness running through the middle, feeding a single main, tail-asymmetrical, but simple. In today's stack, that bar has developed structure. There's a brighter knot on one side of the nucleus, a softer lobe on the other. In a faint arc wrapped around them, a partial ring like a wave caught mid-expansion just beyond. A second, wider arc is visible if you push the contrast, marking an older pulse. It's like tree rings in dust. Each shell is a snapshot of what the comet was doing when that material left the surface. The new inner arc wasn't there in earlier images. It's fresh. Farther down the tail, a subtle fork has appeared. The main spine still stretches away from the sun. But now there's a faint second streamer peeling off at a slightly different angle, exactly what you'd expect if a new jet with a slightly different orientation has joined the existing flow. The coma isn't just active, its architecture's changing. Then comes the part that doesn't care about how pretty the images look: the orbit. Every new position measurement from ground observatories, from heliophysics spacecraft, from wherever they can get a clean detection gets fed into the orbit solver. Gravity handles most of the motion, but this comet is not a dead rock. Its jets act like tiny thrusters, giving it an extra push. The model has to account for that push, which shows up as a non-gravitational term. If the comet were calming down, that term would shrink and stabilize. The orbit solution would barely need to change from one day to the next. Today's solution did not behave that way. Using yesterday's non-gravitational parameters, the predicted positions missed the actual detections in a specific direction. The residuals all leaned off to one side of signature. That the net push from the jets has rotated again. When they let the solver refit the data, it wanted two things: a slightly stronger non-gravitational acceleration than yesterday's model allowed, and a slightly different orientation for that acceleration, shifted in the same direction as the new fork in the tail. That's not noise. That's the dynamics keeping pace with the images. So line up the three main diagnostics. The brightness curve has shifted onto a new track with a different rotational pattern. The coma and tail have gained new structure, fresh arcs, a new fork, a more complex inner core. The orbit solution now requires a reoriented, still significant self-push. All of that is what evolving looks like in data. Now, the question is, what does that actually mean inside the nucleus? The simplest picture is that we're watching the comet peel itself in layers. When this comet tore through perihelion, the outer shell responded first. Loose dust, shallow ices, weak crust. That's when we saw the wildest flares and the messiest coma shapes. But heat doesn't stop at the surface, it creeps inward. Deeper down, the comet's interior isn't smooth. It's a chaotic mix of ancient ices, voids, and fractures built up over billions of years in interstellar space. Each depth has its own chemistry. Each fracture network has its own weaknesses. Each pocket has its own threshold temperature, as that internal temperature wave works its way down. New layers cross their tipping points. One layer activates, and you get a certain mix of gas, dust, and jets. The rotation feels a particular pattern of torque. The coma looks a certain way. Then, a little deeper, another layer wakes up. The composition changes. The dust grains get larger or darker. The jets shift location. Some old vents collapse as new cracks open. The rotation gets nudged again. The orbit fit needs a new thrust direction. From the outside, you see exactly what today's fresh data shows. The behavior is not repeating, it's developing. The light curve is more structured now than in the chaotic early days. Multiple regular peaks instead of random spikes. Because the active regions that survived the first violent phase are now locked in, even as deeper material joins the flow. The coma is more layered, shells upon shells, because each burst from a new depth leaves its own mark, expanding outward and freezing into the overall glow. The non-gravitational term is more coherent, not wildly flipping, but steadily rotating and adjusting because the jets themselves are becoming less random and more organized around a few dominant sources. That's the optimistic side of evolving. A stressed system finding a new configuration. But there's another side. Evolution under stress isn't free. Every new layer that vents adds fresh torque. Every spin-up, even a small one, increases the centrifugal force, pulling on already damaged regions. Every reorientation of thrust means certain fracture zones are being loaded differently than before. We've seen this before with comets native to our own solar system. Some of them passed through their evolving phase and came out the other side as stable, misshapen, but intact nuclei. But others kept evolving, until the structure couldn't keep up. One update, it was a stretched core with complex jets. The next update, it was a string of fragments. Right now, this comet is somewhere in between. It's not the explosive chaos of peak activity. It's not the quiet fade of a spent comet. It's the middle, the part where the outer layers have already been stripped and the inside is deciding how or if it can hold together. Today's fresh data doesn't give us a final answer. What it does say clearly is that this interstellar visitor is not simply dimming and drifting away. It's changing the way it spins, the way it vents, the way it moves, all at once. If over the next few days we see these new patterns stabilize, the light curve locking in, the coma structure repeating, the thrust direction settling, then we might be watching the comet finish its evolution into a new outbound state. If instead, the peaks keep shifting, the shells keep multiplying, and the self-push keeps rotating, then evolving might just be the polite word we're using for a process that hasn't decided whether it ends in survival or disruption. Either way, we're not just recording one snapshot of an interstellar visitor. We're watching it change day by day in real time, and that makes every new data drop matter. Think about what it means to catch something like this in the act. Most comets we study have been looping around the sun for thousands or millions of years. They've settled into predictable rhythms. Their surfaces are weathered and uniform. Their activity curves are smooth. They're like old actors who've memorized their lines. This one is different. It came from somewhere beyond our solar neighborhood, carrying ices and materials that formed under conditions we've never directly sampled. It spent eons in the deep freeze of interstellar space, unchanged and dormant. Then it fell toward our sun for the first time in its existence. The heat it's experiencing now, it's never felt anything like this before. So what we're seeing isn't just activity, it's a response. A violent, unscripted reaction to an environment this object was never designed to handle. And because it's never been here before, it has no memory, no conditioning, no stable pattern to fall back on. It's figuring itself out as it goes. That's why the data keeps shifting. That's why every update brings something new. This comet doesn't know what it's supposed to do, so it's doing everything at once. Venting, spinning, cracking, adjusting. Until something finally gives or settles, we get to watch. The brightness changes tell us the surface is alive. The rotation changes tell us the interior is redistributing mass either through loss or through internal shifts. The coma structure tells us where the material is coming from and how violently it's being expelled. The orbit tells us how all of that adds up into a net force that's literally steering the comet through space. Put it all together and you get a picture of an object under enormous stress trying to reach some kind of equilibrium. But equilibrium might not be possible. The forces acting on it, solar heating, internal pressure, rotational stress, might be too much for the structure to absorb. In that case, what we're calling evolution is actually the slow-motion beginning of something more dramatic. We've seen comets split before. Sometimes it happens suddenly, a single observing session where the nucleus was intact, and the next session, it's two pieces drifting apart. Other times it's gradual. The light curve starts showing double peaks, a coma. Develops two distinct centers. The fragment separates slowly, leaving a trail of debris between them. Right now, this comet isn't showing the classic signs of a split. There's no second nucleus visible in the images. The light curve, while complex, still looks like one object with multiple active regions, not two objects tumbling independently. The non-gravitational acceleration, while shifting, is still coherent. It's acting like one net push, not competing thrust from separate fragments. But that doesn't mean it's safe. It means we're still in the phase where the outcome could go either way. If the internal structure is strong enough, if the active regions vent without breaking through critical load-bearing zones, if the spin-up stays gradual enough that the centrifugal forces don't overwhelm the cohesion, then this comet will survive. It'll settle into a new state, probably spinning faster than it started, probably with a different shape, probably with a scarred and pitted surface, but intact. It'll carry that new configuration with it as it leaves our solar system heading back into the interstellar void. If not, we'll see the signs before it happens. The light curve will start showing erratic behavior, peaks that don't repeat, brightness spikes that don't fit the rotation. The coma will develop asymmetries that can't be explained by a single nucleus. The orbit solution will struggle to find a consistent thrust direction because the pieces will be pushing in different ways. And then one day the images will resolve it clearly. Where there was one comet, now there are two or three, or a cloud of debris with no clear nucleus at all. We're not there yet, but we're in the window where it could happen. That's what makes this moment so critical. We're not watching a comet at the beginning of its journey when everything is still locked up and frozen. We're not watching it at the end when it's far enough from the sun that nothing interesting will happen anymore. We're watching it right now in the middle when it's still active enough to change, but stressed enough that change might mean destruction. And the data we're getting today is part of that story. The brightness sitting above the expected curve means more material is still coming off than the models predicted. The rotation speeding up means the mass distribution is shifting. New structures in the coma mean the venting pattern is evolving. The adjusted orbit parameters mean the comet is still pushing itself in ways we didn't fully anticipate. All of that is normal for an active comet. What's abnormal is that it's still happening this far from the sun, this long after perihelion. With no signs of slowing down, most comets follow a predictable arc. Peak activity near the sun, then a smooth decline as they move away. By now, This comet should be well into that decline. Still visible, still active, but fading steadily. And predictably, instead, it's throwing curveballs, staying brighter than it should. It's staying more active than it should, still changing when it should be settling. That tells us the interior is still hot. It tells us the deeper layers are still sublimating. It tells us the comet is still bleeding energy and mass faster than the surface alone can account for. And that's why every new data drop matters, because somewhere in that interior, there's a tipping point. There's a depth where the ice runs out, or the structure gives way, or the temperature finally drops below the threshold for sublimation. When that happens, when the comet finally exhausts its ability to keep evolving, we'll see it in the data. The brightness will lock onto a smooth decline. The rotation will stabilize. The coma will simplify. The orbit will need fewer and fewer adjustments. But until then, we're in the unknown. And that's exactly where science gets interesting. So, if you want to see whether this interstellar visitor finishes its evolution as one object or many, if you want to catch the moment when the data finally tells us whether it held together or came apart, make sure you're subscribed, stay tuned, and as always, stay curious. I'll see you in the next.